Good morning, everyone. Let's get started. Just a quick announcement. Monday, there will not be any discussion sections because of Labor Day, but we will still have a worksheet and we will have a recording of a walk through the worksheet, so do follow that. Okay. Excellent. Okay, so with that, this lecture, we're going to continue with that broad overview that we started last time of this kind of bottom-up view of the internet. And so we're going to wrap up our discussion of circuit versus packet switching, and then we're going to, in the second half of this lecture, start that top-down overview. And so just a quick recap from last lecture, we said that one of the fundamental questions in networking is how do you want to share network resources? And we said there are two high-level canonical approaches. One is based on this idea that you're going to reserve bandwidth for the duration of your communication. And the other is this idea that you're just going to send your data and hope that the network can handle it. So that's the best effort model. And in terms of how we implement these approaches, we said, again, two canonical approaches. Circuit switching is the de facto way by which one would try to implement reservations. And packet switching is how we implement best effort delivery. Still, a recap of how circuit switching works is this idea that if I want a certain amount of reserved bandwidth between these two blue end hosts, I'm going to take the peak demand or whatever the application needs in terms of a bandwidth in order to have that communication, send a reservation request through the network. It will follow the path that the routing algorithm has picked. And if all the switches along the way can actually accommodate that 10 megabit per second, then we've established what we call a circuit, where a circuit means I have that 10 megabit per second reserved bandwidth for this particular flow. And when you're done, again, the end host will initiate what we call a teardown circuit message, which is kind of like garbage collection. You're basically going along that path saying, I no longer need this reservation. You can let go of those resources. And so that's the basic idea we had behind circuit switching. Packet switching, I think we've done this many times now. You basically have a packet. It has a destination. You send it into the network, and each switch is going to treat that packet independently. So where we got to was this discussion or this question about which approach is better, circuit versus packet switching. And so I'm going to turn to you to give me the answers here. And anytime I ask you which approach is better, the first question you should ask is, what are your metrics, or what are the dimensions along which we're going to compare? And so any ideas? What should be our criteria for deciding which one is better? What matters? Yep. Packet size. Say more. Let me build on what I think you're getting at with that, which is if I have a very large packet, maybe it's not going to make it through. And so a circuit would have been a better way of guaranteeing that I would get the resources I need. Okay? Anything else? Yeah? So how robust is this to how likely is failure going to be, or how likely a drop packet's going to be versus, okay, I thought you were going somewhere else. That's also a valid point. Can I lump those into what kind of service am I going to get? Am I going to get good performance from my network? Anything else we should worry about? Yeah? Throughput. So can I say efficiency? Like how well am I using network resources? Yeah? Remember, internet. Big place. Lots of things that can happen. What else should we worry about as we think about implementing circuit switching or packet switching? Yep. Complexity. Right? Which one's going to be simpler? Which one's going to need more mechanism? Other things. You have 2 out of, I think, the 4 that I had. Fault tolerance? Like which one of them is more robust to things in the network failing? And okay, the next one. So the 4 that I had was, the first, and it's, everyone always overlooks this, but we shouldn't, is this actually a useful abstraction? Right? So ultimately, we're building the internet in order to build applications. And so one might ask which of circuit versus packet switching is a better abstraction for applications. And this is important because that's kind of like the API we're exposing to applications, and so it matters that it's a useful or good API. And they're very different, right? In circuit switching, as an application developer, the abstraction that the network is giving me is you can ask for a certain amount of bandwidth, and if I tell you that you have it, then you as an application, you're guaranteed to have that amount of bandwidth to the end host. Whereas packet switching, on the other hand, or best effort, the abstraction it's giving an application is send data and that's it. Right? The rest is up to you. You may get 10 megabits per second, you may get 1 megabit per second. It may change over the duration of your flow. So very different abstraction. The other one was efficiency, and in particular efficiency at scale. So this was the answers that popped up around how well are you using network resources. Because remember, bandwidth is expensive. Operators deploy links with a certain amount of bandwidth. They want that bandwidth to be well used. Also, efficiency matters because applications, the more bandwidth you can get out of your network, presumably better performance you can get. Handling failures, we've said that the internet is vast. Links go up and down, switches go up and down. Any solution or architecture we come up with has to be resilient to those kinds of failures. And finally, complexity of implementation. Because the internet, again, is a large-scale, complicated system. If you're going to try and engineer something that's incredibly complicated, you're probably not going to get very far with it. Any thoughts on these as goals? Okay. What do you think from an application viewpoint, as an abstraction? If you were an application developer, which abstraction would you like better? Which one do you think is easier to build an application on top of? Yep. Probably the reservation one, right? It's kind of, one, you get better performance because you think about what's the maximum performance your flow needs, what's the maximum bandwidth, and then you have it. It's guaranteed to be there in the network for you. It's also exactly what the point, which is it's predictable and understandable. And if you think about just when you write code, for example, you have a multi-threaded program and you run it on a cloud instance somewhere, whether if you have 4 cores versus if you had 8 cores, or if you had 32 gigs versus 64 gig given to your application, your performance varies. And if no one told you how many cores you were going to have at what point in time, or how much memory you were going to be assigned versus not, it would be very complicated to reason about the performance you'd expect from your network, from your application. And the same is true from the networking perspective. Right? If my available bandwidth keeps changing, that's going to add some complexity to my application and reasoning about application performance. But the other reason is it's actually a very intuitive abstraction as a business model. Right? If you think of it from an operator standpoint, if you had this abstraction, you could say, well, you customer, end host, you asked me for 10 megabit per second. I gave you 10 meg, so this is how much I'm going to charge you. If you ask me for 15 megabits per second, I'm going to charge you more. There's a hook in there to charge based on usage. Right? And if you think about it, that's what we do in the cloud as well. You pay for a 4-core instance, or you pay for an 8-core instance. You pay more for instances with more memory. Why shouldn't we expect the same from the internet? Why shouldn't operators expect to be able to charge based on use? Okay. They're not going to be able to, but it seems very reasonable as a goal to want this kind of abstraction. And that's largely the appeal of circuit switching, is that it seemed like an appealing abstraction. What about which one makes more efficient use of network capacity? Before I go here, actually, let me pause. Any questions on this idea of circuits versus best effort as an abstraction? No? Okay. So efficiency. Which one do we think makes more efficient use of network capacity? Oh, sorry, I thought you were raising your hand. Yeah? Best effort? Say why? Yes, so that's, anyone disagree with that? No, so you're absolutely right. And what I would say is that packet switching is typically more efficient. And that weasel word typically is in there for exactly the reason you were describing, which is it depends a little bit on how bursty your flow is or how bursty your traffic source is. And to see this kind of visually, let's think about one example. Let's say I had a 30 megabit per second link. And I have 3 sources that have flows that they want to initiate reservations with. And each source needs a constant rate of 10 megabits per second. This means throughout the duration of that flow, the source wants to send exactly 10 megabits per second. In this context, packet switching and reservations, both of them are actually going to be equally efficient. Both of them are going to do equally well. Visually, if you want to see that, if I had this pipe with 30 megabits per second and I had 3 sources that were asking for 10 meg each, you can see that the pipe is fully used and every one of the sources got exactly what they needed. So everyone's happy. Right? We have efficiency and we have happy sources. We would have had the same with packet switching. The network just had the capacity to absorb all of the demand. But what if we'd said that those 3 sources look like this, where their demand is bursty? There's a period of time where they have some amount of demand and then it's not actually using the network anymore during the rest of the flow. And that peak usage was actually more than 10 megabits per second. It was 12, 11, and 13. With reservations, what would happen if this was what my sources needed? And here, the duration of the flow is the entire width of this demand that I've drawn here. What would happen if you were running a circuit switch network? Yep. You reserve the peak for the entire thing. For which flows? So let's walk through this. The first source comes along and says, I need a reservation for 12 megabits per second. Right? The network says, that's good. You get to go. The second one turns up and says, I need a reservation for 11 megabits per second. Right? We're still good. I grant the 11. And then the third one comes along and says, I need a reservation for 13 megabits per second. The network no longer has 13 megabits per second available. So the typical option with reservations is that you'll allow 2 flows to reserve their peak rate. That's what they asked. Because the network has no way of knowing that the source doesn't actually need the full reservation over the entire duration of the flow. The network just believes what the source says and hands out that bandwidth. For all the network knows, it's going to be, source 1 is going to be sending at 12 meg throughout. Source 2 is going to be sending at 11 meg throughout. It doesn't know. So it hands out those 2 reservations, but it must turn away the third flow. And so if you think about what's going on in that pipe now while I have these 2 reservations, I have satisfied 2 of my sources, but my network is highly underutilized. It's underutilized both when each of those flows is not using the full reservation, and it's underutilized because I had this leftover capacity that was not enough to actually hand out to any other source. Question? Right. So the question here is that, why didn't the blue source let go of the reservation? This is a particular example where I'm saying the duration of the flow is the entire width in time there. So you're right that if the blue source had torn down the reservation at the end of its demand, where it starts sending traffic, then we would have not had a problem. But that's just not what this example is showing. Okay. Any other questions on this? Yeah? Yeah, so this is a great question. Do people try to actually, do the sources try to make the traffic they generate more efficient in the sense that it will consume the full reservation? In practice, when we talk about MPLS circuits a little bit at the end, yes, people will try very hard to make full use of that MPLS connection, but sometimes it's also the nature of the application. And for example, if this was a web browsing session, the way we browse is, you click on a link, and then you read. There's some quiet time, and then you click on another link, or you click on a video, and then you get, again, more demand. So inherently, depending on the application, some applications are inherently choppy and bursty. There's not much you can do about it. Any other questions? Right. So what would have happened with best effort? Right. With best effort, every source would have just sent their traffic. And if you look at how these sources line up in time, we got lucky. There was plenty of demand. There's no overloading. Every one of the sources is happy. Right? this is actually very much the same as the example we had with statistical multiplexing and why statistical multiplexing works at all. What this example is showing you is that statistical multiplexing works better with best effort service than it does with circuit switching because we are multiplexing at the granularity of packets, not flows. Okay? So this is, in this case, best effort would have made much more efficient use of network resources. Any questions on this? So this is really the broader distinction about, kind of know your workload and the difference between smooth versus bursty applications. And so typically we'll characterize a flow or an application by the ratio between the application's peak demand rate and the average demand that it has. And so a smooth application or some applications will have a fairly low ratio. The peaks are not much more than the average. Streaming media or audio or video are typical examples of that. You don't see a huge amount of variation. So those we would tend to call pretty smooth applications. But others, and famously data applications, tend to be much more bursty. They can have peak to average ratios that are in the hundreds. This also tells you why the old phone network was designed to be a circuit switch network. Because when you place a voice call, they're not typically long silences. Right? You placed a voice call in order to talk to someone, and then when you hung up, you're done. So the idea of circuit switching was actually, it made sense. Because you have this smooth, constant rate demand, and at the same time, you're very sensitive to performance because we hear disturbances in audio. And so it made sense to have that guaranteed bandwidth. Okay. So going back to that question about which one is more efficient, typically packet switching, where that typically depends on the burstiness of your traffic sources. And again, the root cause of why packet switching is more efficient is because we're multiplexing at a finer granularity. Individual packets can come in and fill the gaps as needed. Whereas with reservations, we are multiplexing at the granularity of entire flows, the entire duration of a flow. Any other differences in efficiency? So not just this statistical multiplexing. Are there other reasons why one of the other would be more efficient? Yep. So exactly. Circuit switching, you spend some time to set up the circuit. Right? So imagine if I had an IoT sensor at home. It takes a temperature reading, and every 5 minutes, it sends one reading to the cloud. Totally normal behavior for something like a sensor. So it sends 100 bytes every 5 minutes. It's a very small amount of traffic. Imagine if every 5 minutes I have to set up a circuit, ask for reservation, get the acknowledgement back, send out my 100 bytes, tear down the circuit, all of that work just to send 100 bytes. You're spending much more time and bandwidth than the actual amount of data you had to send. So again, circuit switching is not the best fit for when you have very small amounts of traffic to send. That was it on efficiency. Let's move on to handling failures. Any questions on efficiency before I move on? Okay. So what happens in the event of a failure? So let's say I'm back with my picture where I have this path. This is the green path. This is the path that the routing algorithm picked. Okay. We've not gone into how it does it, but just say the network has decided this is the path it follows from source to destination. What do I do if I have a failure? Right, so this switch went down. Let's think about it first in the context of packet switching. So anytime I have a switch go down, the network has to do something about it. It has to detect that that switch went down, and it has to recompute a different path through the network that avoids that switch that's failed. Okay, so this is, in this case now, let's say that the network, by running this routing algorithm, picked this new path going between the source and destination. So at this point, the network has fixed the problem. It has found a different path. What does the end host have to do if I'm doing packet switching? Yep. Nothing, exactly. The end host has to do nothing. The end host didn't even have to know there was a failure. Now you just send your packet. When the packet reaches that fork green router there, it's going to send it to the new switch instead of the failed one. And there might have been a period of time while the network was busy figuring out this link is down, I need to go this way, and recomputing paths. There might have been a period of time when packets were getting dropped because I had no path. but the end host didn't have to know. Right? So it's as simple as it gets in terms of, from the end host perspective, this is as simple as it gets in terms of fault tolerance or failure recovery. You just send your packets. What about with circuit switching? So again, with circuit switching, the switch is going to fail. The network is going to recompute a new path. It has now found this new green path. What does the end host have to do? Yep. The end host has to send another reservation, right? And the reason is because we had set up this circuit. All the switches had reserved 10 megabits per second along the path. And now one of that switch failed, and the path is going through a new switch. That new switch made no guarantee that it had 10 megabits per second. It has no reservation state. So you have no idea whether that new switch can actually accommodate the reservation or not. Even more, you don't even know that the switches that used to be on the old path are the same switches that are now on the new path. So you also have to free up the resources from the previous reservation. Right? So what you have to do, you have to actually tear down the previous reservation, and then you have to send a new reservation request in, going through the network. And there's even no guarantee that this reservation will work, because there's no guarantee that the new switches along this new path actually have that amount of bandwidth. Right? So to recap, this should start, I hope, to sound far more, circuit switching should start to sound more complicated to you. To recap, failure recovery in packet switching, the link goes down. What do? The network has to first detect the failure. It has to recalculate a new path. This is the job of the routing control plane. And then the end host and the individual flows do absolutely nothing. They just continue sending packets. The destination has not changed. The path has changed, but the end host doesn't need to know about it. With circuit switching, you have to do everything that you did with packet switching, so the network still has to find a new path. But in addition now, the end host has to detect or learn about this failure. It then has to tear down the old reservation and establish a new reservation. And if you think about it, all end hosts that had a flow going through that switch that failed have to do this. So think of this now from the perspective of you have a switch that's in the middle of Google or AT&T's backbone. It has millions of flows. And that switch went down. It took down millions of flows with it. You have millions of sources that have to react by sending new reservation requests. And probably they're all going to do that at the same time, just to make things worse. Right? So it's not sounding so pretty as a fault-tolerant design. Let's move on finally to complexity of implementation. And here I mean a little bit, aside from failure, which one do we think is more complex? And so this is where you're going to start to realize that the design I've given you so far is actually far from being a complete design. We have to extend it in order to make it work. So let's think about that. So what we've said so far is that a source is going to send a reservation request to the destination. And I said, it's going to go 10 megabit, ask every switch along the way, and every switch is going to say, yes, that sounds good. And you can now have a circuit established. But how do the switches actually know that the reservation went through? Like, how do switch 1 and 2, let's say the reservation request went through 1 said yes, 2 said yes. How does switch 2 know that 3 and 4 are going to say yes? How do you actually know that the reservation made it through all the way? It's not a trick question. You have to extend the design. So what new mechanism would you add to the design? Yeah? Right. So let's say the next thing we're going to do is we're going to say this reservation request goes all the way to the destination, and every switch along the way is going to, in the reservation, say yes or no. And if everyone said yes, then the destination is going to send a confirming the reservation message that will travel back to the source. Okay? That's a reasonable extension. So that's how we could say we've extended the design so that the switches know if that the reservation went through. But what happens if the reservation request is lost along the way? So 1 said yes, 2 said yes, but then the reservation was dropped. So 3 never even saw the reservation request. What do we want to have happen? Yep. So we're going to extend the design yet again. We're going to say every switch holds a timer. Right? And that timer, when I accept a reservation request, I'm going to set a timer. And if the timer goes off before I see a confirmation coming back, I'm going to say this reservation didn't make it. And I'm going to release those resources and delete that reservation. Sounds reasonable? Yeah? So what happens if the confirmation that the reservation made it is now lost? So let's say the reservation went through 1, 2, 3, 4. Everyone gave it a thumbs up. The destination is sending the confirmation back, goes through 4, goes through 3. So 3 and 4 now think, great, this reservation is confirmed. And then I drop the confirmation. What do I do? What's going to happen first? Let's step through that. Those timers at 1 and 2 are going to expire, right? So now we're in the state where 1 and 2 don't have reservation state, and 3 and 4 do have a reservation state. What should we do? Yeah. Yeah. So one approach you could have is that 1 and 2 could send out a message saying, my timer expired, I'm deleting this reservation, tear down that state. That's one option. Anything else you could do? That I think is the most sensible option, but there are more. Yeah? Right, so you could resend the confirmation request multiple times, so in the hope that at least one of them makes it through. It's probably no guarantee, but yes. Right? You could have the host have a timer and say, I didn't get a confirmation, so now I'm going to send a cancellation. What happens if you sent that cancellation and then the confirmation came in while you sent the cancellation? So, as you can see, the part I'm trying to get at is not that it is impossible to design this. We can design this, and people did design this. It's that there are a lot of corner cases. It's a complicated system to get right. Okay? So, for example, what should the end host do if the reservation is declined? So I asked for 10 megabits per second, and it was declined. Ideas people have had are, well, you could have asked the switches to tell you what reservation they could have given you. So at least the application source could say, well, I couldn't get 10, but it looked like 8 would have made it. And then you try 8. Still no guarantee because someone else might have booked it while you were in the process of negotiating from 10 to 8. What happens when the underlying route changes? That's all of the fault tolerance mechanisms we described. You have to detect failure, detect change, readjust, repeat your reservation, and so on. So again, we could sit here and design this. People did. They spent years designing this system. But it's hard. Why do you think it's hard? Like, what is fundamentally hard about this problem that we're trying to solve? Yep. Time, asynchrony, the fact that different nodes are doing different things at slightly different times, sure, yeah? Dependencies to make it all work. Yes, build on that a little bit. There's a word I'm looking for. What are those dependencies? What am I dependent on for the reservation to be set up correctly? Right, so the dependency is different systems are setting up this object and they have to agree. So the word I'm looking for is consistency. Right? What we've created with reservations is we're creating state in the network. These switches are creating state. At every switch, you're creating state that says, do I have this reservation or not? So it's a lot of state. It's for every flow in the internet. It's highly dynamic state. Because every time I start or stop a flow, I have to go and create the state. And perhaps most crucially, that state has to be consistent across all of the switches. All of the switches have to agree whether that reservation made it or not, whether that reservation is torn down or not. And if you've, in CS162 or some other class, if you've studied about consensus algorithms and Paxos, you'll know that that is fundamentally a very difficult problem, that in an asynchronous system, having a bunch of participants agree on an outcome is just an inherently hard problem. It requires many rounds of communication and very complicated protocols. Even in contexts like data centers, people make very sparing use of algorithms like Paxos and so on. They tend to be a performance bottleneck. So trying to achieve consensus across the internet at the timescales of flows coming and going with all these uncoordinated participants is just a really hard problem. So just to recap, circuits versus packets, the pros for circuit switching is better application performance because you have your peak rate reserved for you, and it's more predictable and understandable. Pros for packet switching, better efficiency, faster startup, easier recovery from failure, and a simpler implementation for all the reasons we went into. Okay. So what is the internet used today? By default, packet switching. Right? So packet switching is what the internet is based on. That said, there is limited use of a protocol we call RSVP, which stands for Resource Reservation Protocol. You can think of RSVP as kind of the protocol we've been designing here in class. That's the basic idea behind RSVP. Providers use it, but they use it in a very limited way, and it's limited in many dimensions. It isn't exposed to end hosts. So an end host cannot just say, I want a reservation, and have the network give it to them. It's typically, they use it almost to set up state, not so much to actually reserve bandwidth. So it's a very watered down form of the protocol, and it's only typically used within one network. So for example, Google uses it in their global backbone network. What is very common, though, is that you will find people that go out and buy dedicated links, things like MPLS circuits or leased lines. Okay? And what these links look like, the typical use case would be within an enterprise between branch offices, for example. So Wells Fargo and San Francisco might want to have a dedicated link, or what they call a dedicated circuit, to their office in San Jose. And pretty much any enterprise that I'm aware of, a mid-scale to large-scale enterprise, will have a large number of these MPLS circuits or dedicated links. Berkeley has a number of these MPLS circuits, for example. They're quite different from the dynamic reservations we've talked about, though, in the sense that, so one, they're highly expensive. If you want to get an MPLS circuit, it's usually 10 to 20x getting a normal internet connection. They are often statically set up. So if Wells Fargo wants that circuit, someone at Wells Fargo will call AT&T, for example, and say, can I get a circuit for 100 megabits per second dedicated between San Francisco and San Jose? For reasons I've never fully understood, this takes months for AT&T to set up. And then they'll come back and give Wells Fargo this circuit. Wells Fargo will have this circuit for years. Okay. And the assignment is not at the granularity of flows, it's Wells Fargo's circuit. All of Wells Fargo traffic between San Francisco and San Jose might go over that link. And going back to the point someone raised earlier, Wells Fargo will be very careful about what traffic they put on that MPLS circuit because it's expensive. So they'll tend to put high priority traffic on there. And so it's a far cry from the vision of highly dynamic reservations that we've talked about. It's actually more like a non-statistically multiplexed. I went out and bought a link for myself. And it's also pretty painful. If you ask Sarah here, Sarah's had the dubious pleasure of actually trying to set up one of these links between Berkeley and AWS. Took many months and was a painful process. And so one of the things when you go out, for example, on an internship or you're working at a company, they'll tell you, are you on the public internet? What they mean by that is typically if you're working in a branch office, they'll have an MPLS circuit, and they'll also have this connection to the best effort packet-switched internet. And people will talk about, are you on the public internet? What they mean is, are you not using that MPLS circuit? Okay. When I first heard that term, it confused me because I thought there's only one internet. All it means is you're not on an MPLS circuit. So you might be wondering, given everything I've said about reservations and we're not using it, why did we bother talking about it? And isn't it obvious that we shouldn't be doing circuit switching or reservations at the granularity of flows like we talked about? A little bit of history here is, the early internet, when people first built it, was always a packet switch network. And the application it was initially built for was file transfers. But if you start looking at, about the late 80s to early 90s, so the internet went commercial. The government stopped funding and running the internet around the early 90s. That's when everyone in the community, both in research and in industry, thought that the internet should transition to doing circuit switching. And their reasons for this actually made sense at the time, right? Because one, they were saying, well, we're going to transition into being a commercial network. And so ISPs are going to have to charge, and circuits are a much more natural way to charge. The other reason was they believed that the killer app for the internet was going to be voice calls and TV, live TV. And the reasons for that, again, made sense. Users at that time, what did they do in terms of communication? They did voice calls, and they watched TV. And so if you were a network operator, instead of building independent networks to carry voice traffic and to carry TV and then carry data, wouldn't it make sense to have one internet that carried all of that? And because voice and video famously need high-quality, constant-rate traffic, wouldn't it make sense to put circuit switching into the internet so that we can do voice and video? Okay? So that was the reason why everyone believed you needed circuit switching. And people spent 10 plus years in the 90s, this was a hot topic, trying to make circuit switching work. Many of the people who worked on this are people that should be familiar to you here at Berkeley. So RSVP, for example, the protocol I just described, Scott Schenker was one of the people that developed it while he was at Xerox PARC, together with Li Shizhang was the other main inventor of that. Jon Stoica, when his PhD thesis was showing how you could emulate circuit switching to get very tight guarantees on packet delay, so what he called quality of service. That's the result that got him his job here at Berkeley. Nick McEwen is a professor at Stanford. When he was a PhD student here, he developed these circuit switches. He showed how you could build hardware circuit switches that could do circuit setup and tear down very efficiently and very quickly. So he did a number of startups in that space. Cisco acquired them. The standards bodies embraced RSVP. This was how the internet people thought was going to go. But yet it didn't actually happen, and ultimately this vision of reservations and circuit switching is viewed as a failed vision. And if you ask me why, it's all the reasons we talked about, that technically it's a hard design to get right, and there's a lot of complexity. But that's not the full story. We've often built complicated engineering artifacts, over-engineered artifacts. We have many of those in existence. Why do you think, what else contributed to kind of the death of this vision? That's one reason. That's an excellent reason. The killer app turned out to be email and the web, not voice and video. I mean, we have Netflix and Skype and all these things now, but in the late 90s, the killer app was email and the web, no question about it, going all the way up to the 2000s and so on. And, this makes sense when you think about it in retrospect. If you were a user, you had your phone was working just fine, your TV was working just fine. The email and the web were things you could not do without the internet. So that was really the game changer for people. What else? We now do have Netflix and Skype and other things working on the internet. What changed? Why do they work now when before we thought they couldn't work? Yep. That's a fair point. The links, bandwidth went up. We now have much higher bandwidth links. It's hard to get people to change in terms of what they're used to in terms of audio and from packet. Yes, there was certainly an inertia in the sense that but the internet was small still in those days. But you're right, even at that point in time, switching the internet from one model to the other wasn't trivial. Yep. Bandwidth has gotten cheaper. Yeah, the dollar per bit, that's actually a good point. The question about whether circuit switching would have been a better economic model than packet switching, I don't think we actually have consensus on that. People don't really know. In some sense, we never got to try it out. Most people, the assumption would be that actually circuit switching would have made operators more money because they could have more easily charged by use, from higher usage. Whereas today, operators struggle with this. Right? Overnight, people went from using their cell phones to place calls to watching video. And so their consumption of bandwidth went up 10, 20, 100x in a very short period of time, but carriers didn't actually get paid more for it. So the economics around circuit versus packet switching is complicated and unclear, I would say. So I think you folks got everything. The one other thing was people actually rewrote applications to be adaptive. So everyone was used to the characteristics of voice calls or the characteristics of a TV stream. But no one thought, well, what if we changed the way people send audio and video? So for example, now what do you do when you have a bad connection? You degrade the quality of the video automatically. That's what all of these players will do. The same with audio. If you're having trouble, it starts doing things where you can think of it as it sends every packet twice or every packet 3 times, so that you're more tolerant to bad performance somewhere in the network. And so just as there was one community working on trying to make circuit switching work, there was another part of the community that was saying, we're just going to go and rewrite applications. And that group was actually also based out of Berkeley. It was Van Jacobson's group at LBL, Steve McCann, Martin Vetterli, who was on the faculty in EE. They wrote some of the earliest audio and video streaming tools on the internet. This was in the 90s, actually. So this is, I think, useful as a lesson in terms of, we have a mental model often as people who design technical solutions of what the user wants. But sometimes when you hand a user a new technology, user behavior changes. Right? So users moved to email and video. Users became more tolerant of video and audio quality that was variable. There's one other reason why I like to talk about reservations. Do you see something happening in computing ecosystem today that might make reservations more or less relevant? Thoughts? Yeah? So online gaming, I would say some people are even more concerned about things like AR, VR, or your self-driving car, where the repercussions of having to be adaptive, it's a little unclear what it means to have an adaptive self-driving car. This makes people nervous. Certainly when people talk about remote surgery or things like that, they want that guaranteed bandwidth. Any other reason? Cloud computing. And so cloud computing is the one context in which if you talk to cloud providers, this is something they actually worry about. And they have good reason to worry about in the following sense, that when you go run your job in the cloud, you get told you have so many cores and you have so much memory. Right? And you run your application and you know exactly what resources you have, and you can reason about the performance. You don't have the same abstraction because of in the network. So you can say, I want a 1 gigabit network connection, but that's only talking about the connection between your VM and your network interface card, so your first link leaving your server. It tells you nothing about the performance you can expect to see between 2 hosts. And so it's actually, cloud providers will joke where they say when they have a tenant who's seeing bad performance, the first thing the tenant will do is they'll tell the cloud provider, your network sucks. It's the network's fault. And they don't actually know whether it's the network's fault, but the network is the one thing where it's not clear what performance you're getting end to end. And so a large number of cloud providers would say that they're interested in solutions that, not across the internet, that still seems like a really hard problem, but even within a data center, could I get some guarantee or some idea of what bandwidth I have between 2 VMs or 2 servers? Okay. So think about that. How would you solve reservations in that context? It's kind of a fun thought experiment. With that, any questions? Okay. So then let's leave circuit switching and reservations behind. From now on, we're going to live in the world of internet packet switching. And I want to take 5 minutes or so to just do a slightly deeper dive on packet switching and how that works. Okay, so going back to that early pipe view, where we have a pipe and we have packets occupying the pipe, the link, and we were drawing it in this fashion. I now want to look at a switch. And I'm going to say the switch has these 2 links coming in. And all the traffic coming in on those links at that switch is trying to go out on this pipe, on this outgoing link. Okay? So think of it from the perspective of the switch, as these packets are going to arrive at the switch coming in on these 2 links. Right? Is there any problem receiving these packets and putting it out on the link? In this particular example, no. Right? At every point in time, the switch received exactly 1 packet, and there was enough capacity on the outgoing link. There was no overload. What if I had a scenario like this? Is there enough capacity on the outgoing link to accommodate all the packets that I have on the left here? Someone says no. Anyone want to say yes? If I just summed up the packets and I looked at the outgoing link. Yeah, in total, yes. But at this particular point in time, the switch has 2 packets that want to be sent out. Right? So this is a scenario we call transient overload. in the sense that if I looked at the total demand for that outgoing link, I have enough capacity for it. But that at this point in time, because sources were bursty and uncoordinated and everyone is best effort, they just send their packets in. At this point in time, the switch cannot take 2 packets and put it out on the link. So we call this transient overload. This is not a rare event. Because we have bursty sources and packet switching, this happens all the time in every switch. All of the internet, you'll find this kind of transient overload. What would you do to handle it? Yep. Mm-hmm. Right. So now in this picture, we're going to add a queue, and the queue is going to store a packet. Right? So when you had these 2 packets, the switch is going to pick one of them to send out, and it's going to put the other one in the queue. At the next point in time, the switch can now choose, it has a packet in the queue that needs to go out, and it has 2 packets on its links that also need to go out. So there's what we call a packet scheduling decision to be made here. Which of these 3 packets should I choose? And it's a subtle and very cute problem, but we'll get to it later in the semester. For now, we're just going to say the switch picks the first packet that came in. It's going to do first come, first serve. So the switch is going to take that blue packet out of the queue, take the other 2 packets and put them in the queue. At this point in time now, the switch has these packets in the queue. It has no packets on the links. So it's going to do what we call draining the queue. It's going to start draining the queue and send out packets from its queue. And it's going to keep doing this. We had no problem. The queue here was there to absorb transient bursts. Okay? So we have queues in switches, and they're there to absorb these transient bursts. But what if my traffic demand looked like this, and I had a queue? I could still put a queue. Right? It would absorb some of these packets. Right? And we call this situation persistent overload. There's no magic I can do here. I cannot pack all of those packets on the outgoing link. So what am I going to do instead? I'm going to put some of them in the queue, but eventually I'm going to drop packets. Okay? And so this is why the network drops packets, because you can only have a finite amount of buffering. And so if I'm under persistent overload, at some point I'm going to drop packets. So this is one of the, yep, question? Yeah. Yeah, so think of it as I deleted that memory. That I just released that buffer and that data disappeared. Interesting question. What else would you do with it? It's worth a thought. Yeah. Okay, great question. What else could you have done? If you didn't want to drop the packet, what else could you have done? Yeah. Okay, that's also a good answer. You could have sent it out to a different link. If I had a different link, maybe a random link. Yeah, why not? Let's say a random link. Or you could have sent it if you had a different path. That would be what networks do. They'll send it on a different path. What else could you have done? There was a hint of the answer there, but. Mm-hmm. Yeah, so actually how it works is you'll have a certain queue that it's a buffer, it's a memory buffer. And let's say I have buffer space to store 100 packets. And packet 1 came in, I put it in the buffer, and I filled up every one of those entries. It's like an array or something that had 100 entries. And I filled all 100 of them. And now a new packet came in. Right? So what do I do? Normally what I would have done is I would have copied the packet from the link to the buffer. But I don't have space now, so I just don't copy it. Literally, that packet is gone from the universe. I'm going to go back to that question. What else could we have done if we didn't want to drop it? Right. Well, I'm always sending one of them through. The problem is I had 2 to send. So I'm going to send one of them, right? But I was going to drop the other one. If I didn't want to drop, the answer that was sort of there was, could I have slowed down the person upstream? Could I have told the switch that was sending me too many packets, stop sending me so many packets? Is that a reasonable solution? Yeah? You had a question? Upgrade the switch, yes. But that's very different time scale. But yeah, that is eventually exactly what people will do is they'll say, this link I keep dropping packets here, I'm going to go upgrade it. This can take surprisingly long. For example, we're having discussions at Google around a link that they know has been overloaded for months. Other thoughts? Say that again? Yes. So you could have told sources that they cannot send more at more than this rate. So this is kind of going back to the idea of telling the source, hey, slow down. I cannot handle this much rate. And there is actually a protocol that is quite widely used in data centers these days where they have this notion of a pause message or pause frame control, where an overloaded switch will tell the switches upstream, hey, can you pause? It also gets tricky to do, right? Because you have to pause it, then you kind of want to unpause it. So how long are you pausing it for? To what degree are you pausing it for? So this also can get pretty complicated, yeah.
How does two directions work? Are there two different wires or physical things, or is it the same infrastructure?
Right. So the question is, how does a bidirectional link work? Again, this is very much a physical layer thing. Typically, you can have completely what we call a full duplex link, which is I can receive at 100 gig and I can send at 100 gig, and those two are completely independent. This is not as true in wireless, because wireless you have interference. But for all the lectures and what we're talking about, we're going to assume these kind of full duplex links. The two directions are independent. Okay, so just keep in mind, it's a nice observation, a nice thought that you could have had a different design rather than drop. You could have tried to throttle or pause upstream switches. Yeah, question? If I heard the question right, it's how do you choose which packet to drop? Excellent question as well. That is yet another scheduling decision. So just like you have this packet scheduling decision about which packet do I choose when I have to send 3, which one do I choose? It's kind of the complement to which one do I drop. As we talk, again, there's a whole space of things you could do. You could say, I'm going to drop the lowest priority packet, or I'm going to drop the packet that's been sitting around the longest because it's already delayed. What for our model, working model in this class is going to be you drop you tail drop. So you drop from the end of the queue. Yep. Right. So we're starting to design RDMA and pause messages and so on. So you're right. So the suggestion was, could we, in the pause message, give some information about at what point in time we're pausing so that the upstream switch has some idea which packets are not going to make it. And so you have some idea of which ones to retransmit or which ones have successfully gone through. You could. That's not how these protocols work today. There's a fair amount of complexity involved in that. Remember, then you have to actually keep state about individual packets, like which packet sequence numbers you've been sending, which switches don't typically do. Remember that 10 nanoseconds, right? Every time we ask the switch to do more, it's a fair amount of complexity. Okay, I'm going to move on. I want to update our thinking and some of the earlier slides based on the discussion we've just had. We talked about packet delay, and we said it was transmission delay and propagation delay. I'm now going to update that to say it's those two plus queuing delay, because any time you spend sitting in the queue is time delay that the packet incurs. Likewise, going back to that life of a packet so far, we said, packet arrives at a switch forwards the packet to its next hop, and you repeat this until you reach the destination. I'm going to update this now to say the switch can buffer or even drop a packet, and this last step repeats until either you reach the destination or the packet is dropped. Okay? So this is the impact queuing has on the life of a packet. So with that, if you look at this, you should now be able to identify 2 new challenges that we've introduced. And these are going to be 2 additional topics we're going to study. One of them is reliable packet delivery. So we've just understood now that the network can drop packets. One of the common reasons is because you've overflowed the queue or the buffer in the switch. And again, I'm going to use buffer and queue interchangeably. They mean the same thing. But there are other reasons why you could drop a packet. Right? The switch crashed while it had a whole bunch of packets stored in its queue. So again, you could have dropped packets. Or sometimes link technology can corrupt because, signal reasons, you can corrupt a packet. So these are all reasons why you can lose a packet. But the application ultimately wants that data to be reliably transferred. Right? You don't want, depending on the context, you don't want your data to just mysteriously disappear. And so we're going to have to design this question of how do we actually do reliable data transfers given that the network is unreliable. The other question topic, so that reliable transport is actually going to be your second project. That's going to be keeping us busy for a fair amount of time, and how TCP does reliability. The other challenge that should have come to mind is this question of what we call congestion control. Packet switching means that network capacity is allocated on demand. But at the same time, every end host is independently deciding and starting flows and stopping flows and deciding how much traffic to send. And this gives rise to a very tricky scenario where, how fast I send impacts the performance that you see, because we're both going to share a link somewhere. And so we have to come up with a solution by which every end host figures out at what rate it's going to send traffic into the network. And it's going to need to pick a rate such that the end host sees good performance, but it's not harming other sources. And at the same time, we're making full use of the resources available in the network. So it's going to be like a distributed rate selection process. And how do we do that? And how do we adapt to it as flows come and go? So congestion control is a major topic that we're going to spend several lectures on later on in the semester. And so going back to our list of important topics for the semester, it was the list we've talked about before. Reliability and congestion control are the two other fundamental topics I'm going to add to this list. And then what else, just to wrap up that stream, what else are we going to do this semester? A few advanced or specialized topics. Security, I'm going to talk about security throughout. CS161 does a much more in-depth study of security. The internet is full of security problems because no one ever designed it to be secure. Right? It's a sort of one-sentence summary of why we have the CS161, half of it devoted to internet security. The web, how do we organize download content, how the web works? How do we manage our networks in SDN? What else do we have on the path? I've had this fairly simple model of switches. In reality, we have things like firewalls and load balancers and more complicated devices in the network. We're going to spend some time on those. And then we're going to talk about certain specialized networks like cellular networks, data center networks, and so on. Okay, so with that, hopefully you have a roadmap of the topics we're going to cover in this semester. Let's take a 2-minute break, and then we're going to switch gears quite a bit. Thanks. How do you end the recording? Wait. Wait for me so I see. Oh. Thank you. All right, let's get started again. And I'm going way too slow. We're going to switch gears now. We've done with the bottom-up approach. We've done the overview of topics. We're going to take a top-down look at the internet. And as you'll see, it's a pretty different way of looking at it. So I just wanted to start really high level. How do you solve a problem typically? So if you go to an internship or you're given a class project and you're told, here's a problem, go solve it. How do you go about this? And this is not a deep question. It's a more mechanistic question. What steps do you take? Yep. Breaking it down. Anything else? Yep. Google said. Okay, I'm going to ignore that answer. Yes. Perfectly good solution, but not what I was looking for. Yep. Brainstorm potential solutions. Yep. Okay. The first one, define the problem. Right? It's always useful to define the problem. What are your goals? What are your priorities? And then break it down, decompose it into tasks and abstractions. And then finally assigning tasks to entities. Assigning tasks to entities didn't make sense, if you were doing all of the work or you were running it on you're thinking of a single piece of code that runs on your laptop. As you'll see, it's a hugely relevant question when we talk about network design. So let's start with defining the goal. I don't want to spend too much time on this. We've said this many times. The goal of the internet, or the task that the internet has to solve, is to transfer data from one end host to another end host, and to do that across multiple networks. Okay. In a later lecture, we're going to come back and have a more philosophical discussion when we read the research paper about, was this the right goal? What about the other secondary goals and what was the right prioritization across them? We're not going to get into that right now. We're just going to take it that our task, the problem we have to solve, is move data from one end host to the other. What I do want to spend more time on is this question of how do you decompose that task? So now that we know what our task is, how are we going to decompose it into tasks and abstractions? And the question here is really all about modularity. Right? When you build a system, I think Barbara Liskov said it best, modularity based on abstractions is just the way we do things. Right? You break it down, you break down the task into these sub-pieces, and you say this entire component or this entire module, you can interface with it through this abstraction or this API, and you don't have to care about what's inside. How many of you know Barbara Liskov? So Barbara Liskov is a professor at MIT. She won the Turing Award about 10 years ago or more, I think now. She came up with the idea of data abstraction, really the foundation for object-oriented programming. And so for that and her work on programming languages, she won the Turing Award. If you've not watched it, you should really watch her Turing Award lecture, or she has a TED Talk too that's shorter and very nice. It's all about abstraction and modularity and why it matters. So what is modularity? You all know this. We take a system, we decompose it into units, and we say that this entire component, here's the abstraction or API by which you interact with that component. It's crucial in building systems. Right? It's crucial because it gives us this separation of concerns. They're the people that build that abstraction or implement how that abstraction is going to be implemented, and then there are the people that use that abstraction without caring about how it's implemented. Right? This allows us to write code faster. It makes code easier to maintain. It makes code easier to reuse. Right? We all do this all the time. And so it plays a crucial role in computer science and computer systems, even beyond systems, I would say. The trick always is to find the right modularity. Right? And that's what we're going to do in today's lecture and the next one as we go top-down. So we're going to talk about networked systems modularity, and in particular, internet, modularity as we want it on the internet. Okay. The need for modularity still applies even when we're talking about a network or we're talking about the internet. I would argue that it's even more important. Thoughts on why? Why is modularity something we obsess about even more in internet context than when you're writing your favorite application? That's a good point, that if something breaks, if we knew exactly where the abstractions were implemented, we would be able to identify where the issue came from. Yep. The problems are more complex and we need to break it down further. Yeah, say a little bit more about why they're more complex. Yep. Right. So you're all absolutely right. Normal modularity is about how you organize code. And you have your code and you want to decide how you chunk it up, where the routines, the APIs and abstractions and so on. When we talk about the internet or generally any networked implementation, that implementation is not just distributed across many lines of code. It's also distributed across many devices, right? Your end hosts and your switches, and it's distributed across different players. Right? The client is very different from the ISP, it's very different from the server. It's also, in fact, even within the client, if I break it down further, you have your network interface card vendor, you have your operating system vendor, and then you have your application vendor. And because networking or usage on the internet is end-to-end, it spans application on one client host all the way to the application running on the server host, you have to reason about how your implementation is divided across all the entities, devices as well as vendors and entities involved along that end-to-end path. Right? So this is why we think so much about, do we have the right decomposition? So with that, how do we decompose the job of transferring data between end hosts? I'm going to ask you to think about it, but I wanted to start by just giving you an analogy. As you can tell, we like analogies in this class, just as inspiration. It's useful to have a picture to relate it to. So let's say that we had, in the real world, you had two CEOs, A and B, and they want to exchange some nasty message with each other. Right? This is data that's being communicated in the real world. How would they go about it? Let's say CEO A writes a letter to B. It folds a letter, the CEO folds the letter and hands that letter to their administrative aide. The aide puts that letter in an envelope, puts CEO B's name on the envelope, and takes that envelope to FedEx. FedEx then puts this letter in a larger FedEx envelope, puts whatever addressing or secret source codes FedEx needs to know how to send it through FedEx's network, and then ships it out on FedEx's truck. And then maybe it goes on that FedEx truck, it makes it to some distribution center, gets on a FedEx plane, goes on another truck, makes it to the other COB's office, gets handed to COB's aide, and then up to the CO. So if you think about the path that network, that letter now is taking, let's think about the physical path that letter is taking as it travels along. CEO on one side handed it to the aide, to FedEx, across to the world using FedEx, back up to the aide, and back up to the CEO. Right? So this is the physical path that data took. It went down from the CEO to FedEx across the world and back up to the other CEO. That's kind of the physical path that the letter took. But if you think a little bit about how communication is happening, where I mean communication as in who's actually communicating, like understanding the other person, it's almost like we have these layers or these levels. And the peers at one level understand each other, right? And they understand different things. Like the CEO understands a letter. The two CEOs both understood the letter. The two aides understood the envelope with, this letter needs to go to my CEO. And the FedEx infrastructure understands only the FedEx envelope. Right? So peers at the same level understand the same thing in this example. Crucially, no one else needs to. The CEO probably didn't even know it was FedEx. They don't care whether it's FedEx or UPS. That's not something they have to worry about. FedEx doesn't worry about what's inside the envelope. It's not their problem. So you're starting to see, hopefully, some separation of concerns coming up here. The other thing is that the lowest level has the most packaging. So if I stopped that FedEx truck on the street and I took that envelope up, I would see a FedEx envelope. If I opened that up, I would see the aide's envelope. If I opened that up, I would see the CEO's letter. So all of that information was there. It was kind of wrapped multiple times. And it was wrapped in such a way that every level gets to understand only what they need to understand. So that's kind of the analogy. Now think about, with that as framing, how would you break down the internet into tasks? And just to narrow the scope here, I'm not asking you everything on the internet, control plane, routing algorithms. I'm asking you very specifically the data plane. If you wanted to transfer data from one end host A to an end host B, how would you do it? So take a minute just to think about it, and then I'll walk through what the internet actually does. But it's useful. Use the CEO template. See how you would break things down. And so just to repeat, don't worry about control plane tasks like routing algorithms and so on. Okay, I hope you've at least some idea in your head about how you would have built the internet or how you would break down this task. Okay, so I'm going to walk through what the breakdown of tasks is. If this seems completely disconnected or you think it's wrong, stop me and ask me why we're doing it this way. But if I had to start thinking about how I get data from point A to point B, starting at the very lowest level, I have to be able to get bits across a wire. Right? So somewhere I have to know how to make that laser do the right thing or get my radio to send out the right signals. That's to get bits across a wire. I then have to know how to get packets across a wire, this notion of a unit of data, the set of bits that form a packet. I then need to be able to deliver packets across a local network. Let me spend a little more time on this. We've said that the internet interconnects multiple networks. Right? So I can have one network that's an Ethernet network. I can have one that's a Wi-Fi network. I can have one that's a cellular network. If I send a message to the cloud on my phone, I'm probably going to go over the cellular network, then I'm going to go over some ISP's optical network, then I'm going to hit the cloud provider and go through their Ethernet network that they have in a data center. And we said the internet interconnects these networks. So each of these networks has to know how to take this unit of data or packet and move it through its own network. So Ethernet has to know how to get an Ethernet, we call it a frame, but an Ethernet packet across the Ethernet network, or the unit of data across the cellular network. Okay, so that's delivering packets across the local network. And then, each local network is just moving packets across its own network. We need some way of getting that packet to move across different networks. Okay, so that's going to be what we call delivering packets across multiple networks. And that requires a global address. So I'm using the Ethernet network to get my packet across Ethernet, and then I'm using the fiber network to go across the fiber network, but I still need some way of reasoning about how my packet gets through end-to-end. So for example, in the CEO context, the postal address of the CEO, is the global address we all know how to, or the entire postal delivery system knows how to get the packet, the envelope to. And then finally, and this is starting to get internet specific, we said we could drop data, so we need to make sure we can deliver that data reliably. We have to be able to compensate for the fact that the network is dropping data. And then finally, the application, you have to do something with that data. Right? That was the whole point. So in practice, there's two steps here that we tend to combine into one, which is getting a packet across a wire and getting a packet across a local network. And that's because it tends to be the same technology. Right? If I have an Ethernet network that has 4 Ethernet links, it's kind of the same technology to get an Ethernet packet across one link, and then I'm using Ethernet technology again to go across those 4 links. So we collapse that into one, and we just say we're delivering packets across the wire and the local network. Does this look like a reasonable breakdown? Probably doesn't cover everything we want to do, but any questions? Okay, so now let's start to look at that, in a little bit of that context of levels and layers. So in the internet, the organization we have is at the very lowest layer, we worry about the physical transfer of bits. Building on top of that, we have the abstraction we provide is the best effort packet delivery across a local network. So it's across an Ethernet network or across a cellular network. And then we build on top of that to do best effort global packet delivery. And what I mean by build on top of that is, in order to achieve global end-to-end packet delivery, I'm going to use the Ethernet network's ability to transfer a packet across the Ethernet network. And then I'm going to use the cellular network's ability to transfer a packet across the cellular network, and so on. And so I'm building end-to-end delivery out of this building block of local delivery. Right? And that's why the internet interconnects networks. Then on top of global packet delivery, I'm going to do, how do I do reliable data delivery? And I switched 2 things in going to this layer. One, I went from best effort to reliable. We all understand what that means. I'm going to do some work at this level in order to make sure my data is getting across reliably. But I also switched from packet delivery to data delivery. And this is, remember, because we said applications think in terms of data. Right? Like they have that image, that file that they want to transfer. They're not thinking in terms of packets. And so this is the layer where we're going to switch from thinking about data to thinking about packets. This is going to be the layer that takes that data and chunks it up into packets and worries about putting those packets back into a file or putting it back into data. And then on top of that, we're going to have applications. So we call, I'll get you in just a sec. We call this a strict layered architecture. What I mean by that is applications, the abstraction that they build on top of is that of reliable data delivery. Okay, so an application doesn't worry about what link is underneath or exactly how you achieved reliability. It just thinks that it gets reliable data delivery, which builds on top of this global best effort packet delivery. So the layer above the global delivery doesn't worry about how the packet got across Ethernet networks or fiber networks. It just thinks I can get best effort end-to-end global delivery, which builds on top of local packet delivery, as I mentioned, which builds, again, on top of the physical transfer of bits. There was a question somewhere. Yeah. You can have encryption at multiple levels. So you could be encrypting at the application, you could be encrypting on a per packet basis. So we'll get to that in a future lecture. So we call this a layered architecture. Right? So a layer is no different from a component or an element of modularity in any system decomposition. What is different, however, is this strict layering, that when I say I have a layered architecture, one layer can only interact with the layer above it and the layer below it. Right? So it's using the layer beneath it in order to implement its functionality, and it exposes some API or some interface or some functionality that is used by the layer above it. Okay, so that's kind of this strict layering organization. And two layers will only interface through, interact only through the interface that one layer exposes. If this sounds vague, it's going to get a little bit more concrete as we go. But let's keep going for now. Any questions? Okay. So going back to this picture, we said we have this breakdown of tasks. They're organized in a strictly layered fashion. This is why we say when we say the internet has a layered architecture, this is exactly what we mean. Every one of those functions or that layer corresponds to a layer in the internet architecture. So we say we have 5 layers in the internet architecture. L1 is the physical layer. L2 is this best effort local packet delivery. We call it the data link layer. L3 is what we call the network layer. That's this best effort global packet delivery. L4 is where we get reliability and data transfer. That's the transport layer. And L7 is what we call the application layer. This is not a typo. It's actually L7. Just a historical note, in the early days of the internet when they standardized these layers, there was an L5 and an L6. L5, it was called the session layer. Its job was, for example, when you have a browsing session, you have many flows, and they're kind of related to your browsing. One is getting images, one is getting ads, one is getting content. And so they thought we should have a layer that deals with sessions as an aggregate or a combination of flows. And the session layer was going to be where we did that. And then layer 6 was going to be a presentation layer, which is how should users visualize data? How would you help applications with different ways of visualizing data? Those functions totally over-engineered. That's why it's disappeared from use. Those features do exist. People just tend to implement them in the application layer. I had a question, but I won't get it. Okay, let me see if I can get through it in the last 1 minute. Why do we have a transport layer? So we said, going back to the other slide, we said here that we had a layer that's dedicated to doing reliable data delivery. Why not put that in the application? Yep. We actually do reliability end-to-end, so I'm going to, in principle, what you said could have been true. That's not quite how we do it. So actually, I'm going to leave that question for you to think about. Why do we have a layer 4 transport protocol? And we'll pick it up next time. Thanks.